The set of limit points in the finite complement topology. That one? Yeah. So my the finite complement topology, because all of the open sets are super big, every open set is all of R except for a few points. This is an example where we showed actually like 1 over n converges to x for all x in R with R, the finite complement topology. This is something we did in class. So that suggests to me that the set of limit points of any set is going to be all of R, because basically every sequence converges to every real number. Remember, a limit point means, like, the picture you should have in mind of a limit point is one where any neighborhood around the point intersects the set. So a limit point would be, in here, that's a limit point, but also right on the end, that's a limit point. Because the reason is because any neighborhood around here touches the red set in some point other than itself. So when you're talking about the interval 0 to 1 with the finite complement topology, that's this set here. Is it true, for example, let's look at, say, 2 here. Is 2 a limit point of that? The question is, if I put a neighborhood around 2, does it necessarily touch the interval over here? And I think the answer is yes, in the finite complement topology. An ordinary little neighborhood around here, of course, will not touch the neighborhood here, or not touch the interval here. But if I'm using the finite complement topology, remember, an open set means it includes everything except for finitely many points. So an open set around 2 is everything except maybe, a few individual exclusions. But even with individual exclusions, you're going to have to intersect with that set at some point, because the exclusions, there's only finitely many of them. So my answer is, the set of limit points of this is all of R. And the way you should explain that is, choose any point in R, say any x, then any neighborhood of x must have some intersection with that set, because any neighborhood has a finite complement, which means it includes everything except for finitely many points. This thing is still not on, sorry. Pushing the buttons as hard as I can. Maybe this one. This one was on when I came in, right? Whoop. Did it just turn on? Yes. I'm feeling good about it. Yeah, is that helpful? I hope so. Yeah. I think this one is turning on. All right. Good. I'm not going to push any more buttons. Okay, thank you for your patience, and check out the homework if you haven't already. We were talking last time about the subspace topology. We were doing some weird examples towards the end, but I want to give just one more example, which is not terribly weird, but just to refresh our memories about the subspace topology, and then we'll talk about something else. How about, let's talk about, we were talking about subspaces of R. So how about this? Y is this strange set. So this is the interval from 0 to 1, close at 0, open at 1, so these points, and then union with the interval open at 1, close at 0. So it's basically the interval from 0 to 2, but you took out 1 point there, right? So this is 0, 1, and 2. Okay, that's the Y. And I would like to discuss why using the subspace topology from R. And I hope you remember what that means. It means the neighborhoods are original neighborhoods from R that have been intersected with Y. So I want to talk about y with the subspace topology from R. All right. What does a neighborhood in Y look like? Well, it basically looks like a neighborhood from R, which has been intersected with Y. So, you know, you can have like a little open interval here, counts as open in Y. I tried to draw a little. Maybe it's better if I draw it this way. You know, something like that. So, like, for example, the interval from 1/3 to 2/3 is open in Y. That's because it's open in R, and then you intersect that with Y, and you get something which is open in Y. A more interesting example, something which is open in Y but not open in R, would be something like 0, 1 is open in Y. All right. This is not open as a real interval by itself, but it is an open set in Y using the subspace topology. Remember, what that means is that you can write that, I will say, since this can be written as something intersect Y, where the something is open in R. Anybody see how you can do that? You need a traditional open set in R, which when you intersect it with Y gives you that weird sort of half-closed interval. Anybody got thoughts? You want a, you know, something which looks like an ordinary open interval from R, but you get this when you intersect with Y. I am imagining something like, you know, this little blue guy that I drew here. You could make it smaller or bigger. You could make it even go out here, right? Beyond the confines of Y. This set here doesn't have to be part of Y. It just has to be an open interval from R. So what interval could I use right there to make it so that when I intersect with Y, I get that? Yeah. -1 to 1. Yeah, really anything just to the left of 0 and then up to 1. -1 to 1 is the most natural way to say it, I think. Yeah. That, when I intersect with Y, you get just from 0 to 1, but it includes 0. That's the slightly weird thing. All right? So that interval is open in Y. What about the other? The other side is also open in Y. Also, the interval 1 to 2, closed at the 2, is open in Y. Since someone else want to tell me what's, how can I choose a set to make that work? Something intersect Y. A real interval. Sorry, you can't see the picture anymore. Yeah? 1 to 5. Yes, I was expecting him to say 1 to 3, but I would accept 1 to 5. 1 to anything more than 2. 1 to 2.01 would work. It don't matter. All right? Yeah, great. So this 0 to 1 is open, and also 1 to 2 is, those are both open sets in Y. Basically everything else that's open in Y just looks like an ordinary open interval. But these are sort of two weird, slightly weird open sets from Y in the subspace topology. Something that's especially weird about this is, let me draw that picture again. And I will have you notice that in Y, the complement of, let's say, the first weird one that we talked about, what's the complement of 0 to 1? Of course, that 0 to 1 is just like that half, the left half. What's the complement of that in Y? All the points in Y that are not there, it's the other half, right? So the complement of 0, 1 is, you know, I would write this as Y minus 0 to 1. And what is it? It's actually the other half of Y, which would be 1 to 2, like that. All right. So this is that other set, and we said those are both open actually. So 0, 1 is open, and its complement is also open. This is weird. Because, you know, complement is open means that it's closed. That's the definition of closed. All right? Complement is open means closed. So the conclusion is 0, 1 here is closed and open. And the same is true of the other half. 1 to 2, that's also closed and open. Clopen, if you prefer. Also, 1 to 2 is clopen. All right. You should. There's one of those memes. Have you seen the meme with Hitler getting angry and yelling at people in his little room? Yeah, there's one about Hitler learns about closed sets and open sets. When someone tells him that actually it's possible for a set to be closed and open, he gets mad and yells at everybody. Check it out. Anyway, yeah, this is an example of in this space here, those are both closed and open. This doesn't happen in R with the standard topology. Remember, in analysis, standard real analysis, the only clopen sets are the empty set and all of R. But in other topological spaces, you can get clopen sets. All right. Any thoughts about that? This is just one more example I wanted to do of the subspace topology before we move on to something else. A little something else. All right, let's move on to the next section then. The general theme of this chapter, remember, is building new topological spaces out of other ones. So like this is an example where I have R and I also have this set, and I can make that set into a topological space by using the subspace topology on it. The next little section in this chapter this is kind of an important topic. This is the product topology. This is how, if you have two topological spaces, say X and Y, might as well write this down. Given topological spaces X and Y, we can make the product X cross Y into a topological space. And what is the topology we use? It's called the product topology. This is a topology on the product. By combining together the open sets from X and the open sets from Y, you can make open sets in X cross Y. All right. For example, the most obvious and useful example is like R2. I don't know if you ever really thought about this. R2 is actually R cross R. Remember, the cross in set theory means you make pairs out of those two sets. And would you believe me that R2 as a set is actually, this is really the definition of R2 as a set. It is the set of all pairs where the first thing is in R and the second thing is also in R. So R2 is a product of those two sets. And actually, the standard topology on R2 is actually the product of the topologies from R and R. So the standard topology on R2 is the product of the standard R cross with the standard R. And the way that the product topology works is you think of R2 as like two perpendicular axes. Each one looks like R. And what does an open set from R2 look like in the standard topology? We've talked about how an open set in the standard topology of R2 looks like the inside of a circle without the boundary. Or if you prefer, you could think of it as the inside of a box or a square or some other weird shape. All of these things would count as basis open sets for now, it's actually more convenient to think of a basis for R2 consisting of rectangular boxes. All right. This is a standard basis open set in R2. And would you believe me if I told you that actually is a product of an open interval in the x-axis product with an open interval in the y-axis, right? If you take pairs of points where the first coordinate is in here and the second coordinate is in here, you get that box without its boundary, all right? The boundary bit is important, but since these are open intervals, when you do that product, you do not actually get any of these points at the bottom because the vertical factor doesn't include that point, all right? So this, that is a standard basis open set in R2, and the point is these two things here, these are basis open sets in R, all right? And so the way we make an open set in R2 is by taking a product of the open sets from R. That's the way you make a basis open set. Now, every open set in R2 does not look like a square. They can have weirder shapes to them, as we know. But the basis sets look like squares or rectangles. They don't have to be squares. All right? This is the basic idea behind the product topology. You get open sets in the product by just doing products of open sets from the individual pieces of the product, the factors. So I'm going to write that as a definition in general. So given topological spaces x and y, first of all, x cross y, let this be the product. This consists of pairs where the first thing is from x and the second thing is from y, right? And the product topology, this is what I really want to talk about, is generated by the basis, and the basis for the product topology is all sets which look like this, U cross V, such that U is open in X and V is open in Y. All right, this is the basis of the product topology. So the way to think about this is open sets in the product look like a little product of an open set from the first part plus an open set from the second part. Although there's a slight technicality, so this is little just something to keep in mind. Not all open sets look like, if you do a product like this, you basically get things that look like rectangles. That's what a product does. At least if you're taking products of things that vaguely look like R, you get things that look like rectangles. But my little note here, not all open sets look like rectangles. It's just that that's a basis. So you can make open sets that are round or whatever, that are not actually products of open sets, but those rectangles make a basis. Not all open sets look like rectangles, but these are a basis. So the fact is, any open set in the product topology can be shrunk down to a rectangle. That's that's what it means to be a basis, remember. All right. Not all open sets look like rectangles, but the rectangles form a basis. Okay. So for example, in R2 with the standard topology, this circle is an open set. This is open, even though it's not a rectangle. It's not like an interval down here crossed with an interval up there. So even though it's not equal to U cross V, right? Because it has a round shape to it. But the fact is, it's still an open set because around any point in here, you can surround any point in here with a little rectangle, right? That's if I'm taking the rectangles as the basis of my topology. It is an open set, not because it itself is a rectangle, but because every point in there has a rectangular neighborhood around it. All right. We're about halfway done. The rest of class is going to be like a bunch of pictures. I hope you like interesting looking topological pictures. Thinking about the product topology in R, R2, and some higher dimensions, R3, I guess. So let's just talk very briefly about visualizing a product. A product of two sets, for example, 0, 1 cross 0, 1. What is that? When you have just two sets there, if this is X and this is Y, right? I would say you want to imagine the two sets as perpendicular to each other. And then I'm going to write this and then I'll draw a picture. Each point of X is attached to a copy of Y. So what I mean by that is, if I take 0, 1 cross 0, 1, it looks like I'm going to draw the first one down here. This is 0, 1. I'll call that X, 0, 1. And then I'm going to draw the second one over here as if it were perpendicular. This one is Y, which is also 0, 1 in this simple example. And then, of course, when you take the product, it's not just those two lines. You get all the points which have X coordinate in here and Y coordinate in here. Another way of thinking about that is just every one of these X values has another whole line of points on it. All right? And these are not actually separated. They are everywhere. Every X value has an entire copy of the set of Y values. That's what this is a weird way of visualizing what a product is, but actually this way of thinking about it is helpful when you're trying to imagine what other types of products look like. All right. This is what I said. Imagine the two sets as perpendicular and each point of X is attached to an entire copy of Y. Or you could think about it the other way around. You can think each point of Y has been attached with an entire copy of X. It's equivalent. All right. But I'm imagining so what you end up with is a unit square. But in this way of thinking about the product, the whole square consists of sort of infinitely many individual vertical line segments that are all packed together. All right. This is my way of thinking about what does 0, 1 cross 0, 1 look like. In a similar way, I could think about what is 0, 1 cross 0, 1 cross 0, 1. You can do more than one factor of the product. The way that I'm going to imagine this is think about that first as a unit square. And then I need to attach another interval to each of those points. So I am going to try to think of the unit square as being arranged perpendicularly to another interval. And this you sort of have to draw in 3 dimensions. So I'm going to draw, this is like an R3 drawing. I'm drawing my unit square in the XY plane. And then each point of that unit square has an extra interval glued onto it perpendicularly. So I get another interval here, 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 and they kind of go up here. And you get this whole box here. But I'm thinking, again, I'm thinking of this box as being made up of a square at the bottom, and then every point on the square at the bottom has one of these sort of toothpicks sticking up from it. Yeah.
The cube is like filled in. It's not hollow.
Yeah, right. It's the entire inside of it, just like this square is filled in. Yeah, I'm getting all of these interior points there. All right. This is a way of visualizing what these products look like. What about this? This is back to 2 dimensions. 0, 1 cross 0, 1, but without the endpoints. What would that look like as a set? So this time, I'm going to draw, that is basically, it's like that square, only what precisely is the effect of the endpoints is what I want to think about. I have this time an open interval in the horizontal direction, an open interval in the vertical direction, I'm going to sort of draw what we get over here. What we get over here is every one of these horizontal points has a vertical bar attached to it, but you don't get one on the two horizontal ends. So what it means is basically I get a bunch of these guys, right? But I do not get the one on the very end, on the very left side, and I also do not get the one on the very right side. Because I'm attaching an interval vertically onto each point of this, but this what I start with doesn't have its two endpoints, and so when I stick all those guys in there, you don't get one on the far left and you don't get one on the far right. And then each of these individually has to be a copy of Y, this space, and so each of these individually does not include its top point or its bottom point. And so that means I also don't get anything on the top and anything on the bottom. So what you get is a square without its boundary. All right. So thinking about the endpoints gives a somewhat weird shape. Here, I'll give you a moment. Think about this. What does it look like if you do this? I mean, again, it looks like a unit square, but the boundary is a little weird. So try and think about exactly which parts of the boundary should be filled in and which are missing. Start by drawing that picture. I give you 1 minute to think about it. Well, your 1 minute is up. Was that enough time? I don't know. You get a box, right? So there are like all of these sort of points on the inside. They're all in there. It's just a matter of the four sort of boundary lines. Which ones are any in there, or which ones? Do you want to say? Maybe someone I haven't heard from yet.
The left vertical one is in. The right
Yeah.
one.
I think we do get the left vertical line. Make sure, by the way, I said 0, 1, cross 0, 1. The way we typically write that is the first one becomes the x-axis, the second one becomes the y-axis, although that's a convention, I suppose. But yeah, because this point is in there, it means you do actually get this vertical bar on the left side. You do not get the one on the right side. So sort of on the right side, you have an empty boundary. What about the top, across the top and across the bottom? Do you get those lines or not? They're saying no. No, you do not, because this, the vertical thing, each one of these individual strips lacks its top and bottom point. So you do not get the top or the bottom line, all right? Did anybody think about specifically this corner? Is that corner in or out? Is that part of the set or not? She says no. Why not?
Because the top, it's part of the top line.
Yeah, that point, well, okay, yes, but it's also part of the left side. So, who wins? Anybody have a strong opinion about this? It's a little, like when you just draw the picture, it's a little ambiguous about that point. The basic principle is each of the original points on the x-axis has one of these stuck onto it. So the line on the leftmost edge of this square is one of those. That means it does not have its top or bottom endpoint. All of these vertical lines look like those. So even the one on the left end does not have the point on the bottom. So to be unambiguous about it, I would do something like that. All right. We do include the left line, but not its endpoints. Okay, great. There were some fun examples of intervals. Some more interesting shapes. How about S1 is going to be the unit circle. S is for sphere. The standard sphere in topology is usually called S2 because the surface of the sphere is a flat, not really flat, but two-dimensional at least. S1 is called is what we call the unit circle. It's like a one-dimensional version of the sphere. Okay, what about what is S1 cross the interval look like? S1 cross the interval. So if I think of S1 as a unit circle in R2, then I could draw the unit circle in R2 as like part of the XY plane and then attach an interval perpendicularly to it. So this is, if I have this is R2 here. I begin with the unit circle, which I'm going to try and draw kind of slanted. That's worse than slanted, but that's supposed to be a unit circle lying on the floor in R2. And then we attach interval 0, 1 to that in the perpendicular direction. Can anybody say what shape will it look like? There's a name for this shape that you all know. It's a cylinder, yeah. If you vertically attach intervals to each point of the circle, what you get is a cylinder, right? This is going to look like nothing when I'm done drawing it, but it's like that. It's a cylinder. Makes a cylinder. All right. Now, this is a cylinder which it's not like a solid cylinder. It's just the outer ring. It doesn't have a cap on the top or on the bottom. It's like a tube without any thickness, I suppose. All right. It's just the points around the cylinder. All right. This makes a cylinder. Now, sometimes it's more convenient, I'm going to say, or this is going to look different, but it actually turns out to be topologically the same. So this is topologically equivalent, although it's going to look different when I draw the picture. You can just draw your whole picture in R2. And this is going to be a little weird, but instead I'm still going to attach the little intervals. I'm still talking about S1 cross the interval. I'm still going to attach the little intervals perpendicularly to the circle, but I'm not going to go up each time. I'm going to go out. It's kind of like if you're perpendicular, but like you're using polar coordinates or something. You can glue intervals onto the circle in that way also. Just make them go outwards. All right. What is that going to make in terms of the shape of this? It makes like a ring type shape, right? Like a flat, letter O with some real thickness to it. Now, topologically speaking, these are the same shape because really this shape, this O-type shape, is what you get if you had the cylinder and if it was slightly stretchy and you just kind of stuck your hands inside it and flattened it down onto the plane. It would look like this. All right, so that's the sense in which they are topologically equivalent. This shape has a name. Anyone know the fancy mathematical name for this shape? This is called the annulus. The annulus is it's like a circle with some thickness to it. That is the annulus. And this one, because it's a closed interval here, this is a annulus with the boundary. That is the outer circle and the inner circle are actually included as part of this set. If this had been an open interval, then those would be excluded from the set, and you would get I would call this the closed annulus. There's an open annulus too, where you exclude the boundary circles. All right, that's an annulus. How about, I got one more fun shape here. What about S1 cross S1? I don't know if you ever thought about this. Can you start with a circle and then glue a circle onto each point of the circle? That's what I want to do. This is actually, I can remember as a young lad thinking about S1 cross S1 for the first time. It kind of blew my mind. Actually, this is a shape that everybody knows about. It's like, so the annulus, I started with a circle and then added a little interval to each point. This time I want to start with, now you have to draw this in sort of a R3 type picture, but I'm going to start with a circle here. And now, around the circle, I'm going to attach on each point another circle. So for instance, right over here, maybe I will, and I'm going to do it in a similar way to this. I'm going to kind of make the circles that I attach go around in a circle so they don't bump into each other. So here's a circle here, right? Every point gets a little circle on it. It's pretty poor, it's difficult to draw this. Can anybody say what kind of a shape does that make if you glue circles around the edge of a circle like that? This also is a shape that you can recognize. Yeah.
Does it make like a donut?
Yeah, it makes a donut shape. All right? We are doing circles all the way around. That's called the torus. So this is a bad drawing of a torus, but this is the idea. All the tops will kind of line up, all the bottoms will line up. It gets worse every time I add anything onto my picture. That's a torus, all right? S1 cross S1 is a torus. It's not S2. S2 is what we call the sphere, but S2 is not S1 cross S1. Unlike R, R2 is actually R1 cross R1, but it's not. Here's a little pro tip, which I offer free of charge. You can amaze your friends by drawing a torus well. This is not a good drawing of a torus. You ready for a good drawing of a torus? You will look like a drawing, an artist. Check it out. Start with that. You with me here? This isn't going to look like anything until the magical stroke. Then, a little smiley like that. You ready for this? This is the good part. Anybody can do it, and it looks great. That's how you draw a torus for your friends. Do the smiley part and then the little frowny part, I guess, on top of it. All right, that's a torus. And you can see where are like the S1 cross S1, where are they? Well, sort of one of them represents the inside ring, and then there are perpendicular rings, all the way around. I'm going to ruin my beautiful picture by drawing this in. But that's how you visualize the torus as a product of S1 cross S1. You have the central circle, plus that circle has these other circles around it. All right? All right, I thought it might be fun to talk we've only got 7 minutes remaining, but let's talk about, this is still generally about drawing pictures, but let's talk about some non-standard products. So I would like to think about what do open sets look like in, how about that or this? RL, remember, means the lower limit topology. So when I do a product, RL cross R, it basically looks like R2. As a set, it looks like R2. But the open sets are not the standard open sets in R2. So what do open sets look like in these things? You have to, actually, we kind of talked already about some of these. You have to think about what does it look like when you take one of these lower limit intervals and do the product with an ordinary interval. Actually, that we did talk about this. So for this one here, you want to think about something like that cross with that, right? This is what a typical open set in the product RL cross R will look like. It's a interval with its lower limit product with an ordinary interval with ordinary open interval. And this, we drew this picture before, right? It's this in the x-axis and this in the y-axis. And so the result is one of these on the left side and then no other boundary values plus all the interior points. All right, so this is a typical, this is actually a basis open set in RL cross R. All right, because this is the product of two basis intervals from each of the two places. What about RL cross RL? Can we try that? So this one, how about RL cross RL? That we will use two different intervals, both of which have their lower limits in them. Two different intervals. So this would look like, 0, 1 cross 0, 1. All right, so one of those, and vertically the same type. It's again it's gonna be a box with all the inside points. Really the interesting thing to talk about is what about the boundary lines? Which, if any, of the boundaries do we get? Anybody feel like, can we say, first of all, what about the line on the left side? Is that missing or is it in there? They're saying yes. The thumbs up means there should be a line on the left side, right? Do you get the whole line, like including its top and bottom points? Which points on the line do you get?
The bottom.
Yeah, just the bottom point, not the top point. That's because every vertical line here is supposed to look like one of these. So the one furthest to the left does include its bottom point, but not its top point. All right? Can we say, maybe, to me it's easiest to think of the two verticals first and then the two horizontals. So what about the vertical line on the right side? They're saying no. Yeah, there is no vertical line on the right side because the x-coordinate is missing on the rightmost side. So there is no nothing right there. All right? Now we can talk about the tops and the bottoms. What about the bottom? Is there a line going across the bottom? I think the answer is yes, because this point is included on the bottom. I've got to do updates. My admin has set a deadline for the updates. You know what I say to that? X. So there is a line across the bottom, right? That's what I was saying. There is a line across the bottom. Oops. Does it include the point on the right? The rightmost end? No. This line across the bottom, in fact, you could think this line across the bottom is supposed to look like one of these. So it does not include its point on the right side. So this goes across the bottom, but omits that point. And what about across the top? There's no line at all across the top because the top left, the top y value is missing. So we get that. And of course, the upper right corner is also missing. All right? So what's the difference between RL cross R and RL cross RL? Well, they're different, I guess. I mean, the open sets here have the line on the left is in there, but no other boundary values. And here we get sort of the lower left corner of the box. All right? They are different. We're going to do some more examples like this next time. Maybe that's a good place to stop. All right. I'd be happy to talk some more about the homework if anybody has more homework.